Greetings, Astronomy 10, and welcome back to Chapter 5. This will be the second lecture about Chapter 5 in our textbooks. Last time we talked a little bit about how molecular clouds and nebulae condense over the course of time, sometimes spurred on by a supernova or something like that, sometimes just from free fall contraction. And eventually they gravitate from a large cloud into a smaller object, eventually forming a protostar at the core with an accretion disk around it because of conservation of angular momentum and the linear momenta canceling out from collisions and such. I wanted to give you sort of just a brief rundown on last time, just very quickly. Just to sort of start things off today. Eventually, the object at the very center should, if there is sufficient pressure and temperature in its core, it should sort of ignite, so to speak, and begin nuclear fusion, turning hydrogen into helium, and becoming a star in the process. And that's basically how a solar system should start, right? Now, if that is true, if all that is true, then there should be evidence, and we saw some of that last time, right? We saw that there were, in fact, some objects that match that description: dark bands, disks of gas and dust, with a high-temperature object in the middle that's ejecting material from its poles, right? Protostars and accretion disks. And so we found evidence of that, right? Now, if that's true, then there should be some evidence of this in our own solar system as well, right? I mean, it stands to reason we have a solar system, and so if things were supposed to have developed this way in other solar systems elsewhere, it should have happened here too, because we can't possibly be special or different somehow, right? This is how things happen. Gravity works the same way in every part of the universe, and the universe is made up of the same stuff: 75% hydrogen, 25% helium. So there has to be evidence of it here, too. So if that's true, it should be somewhere that we can find it, probably, right? Now, I'm going to define some terms for you, because these will become more important as the lecture goes on, and I'm sure you'll be able to see why that is exactly, right? There's this thing, a meteor. There's also a meteoroid and a meteorite. Now we have to be really, really careful about these and not confuse one with the other, right? Because some things can only do certain things. Like a meteor, for example. I know it's tempting to think that a meteor is a rock, but it's not. A meteor is like a flash of light, a streak of light that you see across the sky. Easier to see at nighttime, of course, unless you're talking about a really, really big object like the Chelyabinsk meteor that struck in, I think it was 2013, the one that blew out windows and stuff in Russia for many, many kilometers in radius because it was a huge piece of rock and landed with a tremendous amount of kinetic energy. With a huge crater. Yeah. But the light that you see, when you see like a shooting star, that's a meteor. Okay? Now, probably everyone has seen a shooting star. If you haven't, I've left a link to a video in the lecture notes and also on the lecture page for today's lecture. So you can kind of see what meteors or shooting stars look like as they cross the sky. Okay, there are also meteoroids, and a meteoroid is a rock in near-Earth space, okay? Like a rock, out in Earth's orbit or something like that, or somewhere kind of near the Earth. That's a meteoroid. Now, those two things are not to be confused with a meteorite, which is what gets left over if one of these meteoroids goes through our atmosphere and makes a meteor streak across the sky and doesn't burn up all the way and makes it all the way to the ground and crashes. Most of the time, if you see a meteor, most of the time you're talking about rocks that are like the size of a grain of sand and they just burn up all the way coming into the atmosphere. And they just disappear, right? So most meteoroids are very small, right? And they burn up when they make their meteor streaks, their shooting stars across the sky. But if any of that material survives when it hits the ground, it is a meteorite. Now, there are plenty of meteorites here on the surface of the Earth. There were more in the early solar system when there were tons and tons of smaller rocks and things out there in the solar system, right? Remember, we started with a big cloud of gas, and then from the gas, little bits of gas and dust would stick together from static electricity, and that would stick to other chunks and make, a tiny little like pebble type structure, and that would maybe hook to another one from friction, and then eventually you make a little rock, and that smashes with another rock, and you make bigger rocks, right? Well, if you look at the sixth image in today's image bank, what you see is a cross-section of what we call a chondritic meteorite, right? It's chondritic because it's made out of chondrules, these little tiny rock chunks, right? Rock and dirt or dust or whatever. If you remember, we mentioned that last time. And you can very plainly see that there are lots of tiny little chunks that make up this rock, right? And so those are our chondrules making up a larger meteoroid, right, which eventually crashed to the Earth and became a meteorite. Pretty interesting, right? Now, not everything is the same size. Some meteoroids can be real small. Some of them are, like the size of a grain of sand. Even still, now, even though our solar system is like 5 billion years old. But in the early solar system, it was all just gas, and then lots and lots of the gas made smaller chunks, right, of gas and dust, and then that made, some small rocks, and then the small rocks collided and made bigger rocks, and then eventually there were lots and lots of small rocks everywhere. But in the early solar system, small rocks would bang together to make bigger ones, and eventually they would get really, really big. You would have huge asteroids that would smack into other asteroids, and eventually you could maybe make really, really big objects, right? Now, if you have something that's really, really big, such that it can hold itself together by its own gravity, that is called a planetesimal. Like planet, it's supposed to be an A, like planet, right? So when you have enough rocks that they can hold themselves together through gravity, then you have what's called a planetesimal. And eventually, if some object kind of sweeps up, so here's, this is to be like a top view of the accretion disk, right? The protostars here in the middle. And then, you have chunks, and those make bigger chunks, and there's big chunks all over the place. And eventually, if one thing is really big and it sweeps up kind of all of the material at this kind of distance from the companion star, right? All of this material gets swept up into this one object. That's called a planet. Now, sometimes these planets have moons, of course, sometimes multiple moons, and the evidence is found in the craters of these objects, right? If you look at the surface of non-geologically active bodies, right, like the moon. The moon doesn't have any volcanic activity, doesn't have plate tectonics. It's not constantly rewriting the surface like the Earth is, right? Things aren't shifting around. There's no earthquakes. There's no volcanoes. And so the Earth is constantly changing the way it looks. Has been doing so for billions of years. But the moon, not so much, right? It's dead now. There is no volcanic activity. And so there are craters that have been in there for a very, very long time. Now, if you kind of look at the solar system overall, you'll see a lot of the material that made up, these rocky planets all kind of in the center of the solar system, right? At the very center, of course, is the sun, and that's mostly hydrogen gas and, about a quarter of its helium and a tiny smattering of some other things from the other 7 point something billion years since the Big Bang happened, right? Stellar processing making slightly heavier elements. But towards the inner part of the solar system, mostly we have lots of heavier elements, things like that, right? Like in the inner solar system we have metals and all that kind of stuff. And mostly the reason for that is obviously closer to the star it's going to be hotter, right? And when you have this huge cloud of gas that has, maybe just a little bit of like iron and nickel and platinum and blah 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 in it, right? Mostly it's going to stay gaseous and evaporated if this material is too close, right? Let's say you've got something that has like a really, really low boiling point like ammonia or something like that. That doesn't really condense out of the molecular cloud until way, way further out. And as a matter of fact, we mostly only see ammonia in forms that's not just purely gas out past like the orbit of Jupiter, like way out farther in the solar system. But then things like metals, right, nickel, iron, stuff like that, require a much, much higher temperature in order to try to vaporize, even in the vacuum of space where air pressure, gas pressure, whatever you want to call it, is really, really low. Vapor pressure actually is probably a better word for that. There's no real air in space, right? Air is an Earth phenomenon. Air happens here because of all the geologic and biological processes that happen, right? Plants make oxygen from carbon dioxide and so on. But in any case, partly because of gravitation, but mostly because of the temperature, we see a lot of metals and stuff in the inner solar system. And then we see different, what we call more volatile materials out in the outer solar system. So they can condense at a lower temperature out of this molecular cloud that made up our accretion disk and our protostar and eventually our star. And that's why in the inner solar system we have rocky, what we call terrestrial or Earth-like planets. And then in the outer solar system we have these big gas giant planets. Jupiter, Saturn, Uranus, and Neptune are just big balls of gas, right? They're not made up of lots of rocks and metals and stuff like that, like in the inner solar system, because all that material, all of the volatile materials have been mostly evaporated out of the center of the solar system, right? The place that's close to the sun. And eventually we ended up with rocky planets in the interior, and then there's kind of like an asteroid belt. And then further out we have these gas giant planets, which have moons, of course. A lot of these planets, Jupiter has something like 67 moons, and a lot of which are actually rocky, right? But the planets themselves, not so much, not out in the outer solar system. Now the net result of all of these processes, right, planetesimals forming to make planets and all that, is a solar system where most of the matter is in the middle, right, because of gravity, right? That makes our star, and our star, our sun, is something like 99.99% of all the matter in our solar system. The rest of the matter form planetesimals, and those form planets, and the near planets are made of rocky or dense materials, while the outer planets are made of lower density materials like ices that only form at lower temperatures. Now, we proposed a model for how this solar system formed. Right, Ninja Meows? What? Smell like lemon or something? What's the matter? And we looked for evidence of it out in the universe. And it would be foolish for us to think that we're at some special place in the universe. That's geocentric thinking all over again, right? We're not at the center of the universe. We can't be special. And so the way that our solar system formed had to be the way that other solar systems formed. And what that means is that other solar systems should also have planets then too, right? We can't be the only solar system in the entire universe that has planets. That's crazy talk. That's ludicrous, right? Now, if that's true, how could we possibly go about finding planets orbiting other stars? Now, that's kind of tough, right? And if you want to just pause it here and think about it for a minute, try to think what you would do if you were an astronomer or an astrophysicist and your job was to try to figure out a way to look for planets orbiting other stars, right? Remember, planets don't make their own lights, unless maybe, you have a civilization like ours that puts huge lights that are, visible from space on the top of casinos like the Luxor in Las Vegas, things like that. But even that's not really that bright. You probably wouldn't be able to see that from, several light years away, or hundreds or thousands or whatever light years away, right? It's not that bright. And so generally we can only see the light from the star that this planet is orbiting. Anyway, give it a thought, hit pause, come back when you're ready. So, there's something called the Doppler effect that's responsible for the way that a car sounds as it drives past you. Everybody knows what that sounds like, right? It goes, eeeow. Why does it sound like that? Well, there are two images in today's image bank. It's the 12th and 13th ones about the Doppler effect, right? The first one shows a car, and the way that it's drawn is basically like this. So let's say, here's your road. This is my awesome drawing of a car. Everybody ready? I'm not even going to try to make it any, I don't know, maybe I'll try just a little bit. There we go. Got a windshield. Yay, we've got a car, okay? Now, this car is moving with some velocity. Let's say this person is traveling at, some decent kind of velocity, something like 30 meters per second. That's like 60 miles an hour. Okay? Now that's about a tenth of the speed of sound. Actually, I think the speed of sound in air is something like 343 meters per second, so it's a little less than that. But it's a not insignificant portion of the speed of sound, right? Some small percentage, close to 10%. Okay? So what that means is, if you're standing next to this car and it's just sitting there in neutral revving its engine, what you're going to hear is the sound waves that it generates just kind of passing you, right? And it's going to sound like one tone. It would be the same thing if you were in a car next to it, right? Just driving kind of at the same speed, you would hear like one steady tone. But now let's say that this car is moving relative to you, right? It's driving down the street, and so because it's moving in the same direction that the sound waves are moving on this side, right? It's going to move here, and then it's going to generate a sound wave, and then by the time it generates another sound wave, it's going to have moved some, and so it's going to seem like that sound wave is bunched up a little bit on this side. But on this side, the sound waves are going to be further apart, right? And so as it continues to move, the sound waves on this side are going to bunch up. The sound waves behind it are going to stretch out. Now what's that going to do? Well, let's say that this car is driving towards you, right? Now we've got sound with short wavelengths. And if a sound has a short wavelength, it has a higher pitch, right? It has shorter wavelength, it has a higher frequency, and that basically is a higher pitched sound. Which is why when the car is coming towards you, it sounds like ee. But as it drives past you, the sound waves on this side are going to be stretched out, right? And if the sound waves are stretched out, the wavelength is longer, the frequency is lower, it has a lower pitch, right? The lowest pitch that human beings can hear is about a 20 hertz bass hit. But the highest pitch sound that we can hear is a really, really high screech that, doesn't really feel good on your eardrums. It's probably something close to 40,000 hertz or 40 kilohertz. Right? Really high pitched sounds have short wavelengths. Really low pitched sounds have long wavelengths. And so as the car is going towards you, and then as it goes past you, right, as the sound waves stretch out, the pitch drops, which is why it sounds like we call this the Doppler effect. E-F-F-E-C-T. That's a little embarrassing. Let me just clean this up. E-F-F-E-C-T. Now the Doppler effect doesn't work just for sound, right? It should work for any wave, as long as you're talking about an object that's moving in some kind of significant or detectable portion of the speed of the wave itself, right? So if like a star moves at some really small portion of the speed of light, as long as we can detect the difference, right, we should be able to tell how the light from this star is Doppler shifted. And if you look at, I think that's like the 14th one, there's two Doppler images. One of them is about light, right? And that one will show light kind of coming this way. Let's erase the people because, you don't want to be out in space, right? So now instead we have like a star, right, like the sun. And if the sun was moving this way, then the light waves would get bunched up, the wavelength would decrease, the frequency would increase, and the light would shift towards the blue end of the electromagnetic spectrum, right? It would get bluer in color. And so we call this a blue shift. The converse, of course, is true. If a star is moving away from you, then you would see a red shift. Actually, this is one word. Red shift. I-F-T. Okay. Now, long story short, if a star is moving towards you, the light should shift towards the blue. If a star is moving away from you, it should shift towards the red. If there's a planet that's moving around this star, then it should oscillate, right? Now, I know what you're thinking, that stars are much, much more massive than planets, and planets, regardless of how far they move, aren't going to move a star that much. But if you consider the Earth, right, the Earth probably isn't going to move the sun that much, but Jupiter, because Jupiter is so much bigger and more massive, it's probably going to move the sun a little more, right? And as a matter of fact, we can kind of tell by how much a star's light shifts and with what frequency, right? You can tell how far a planet is from its companion star by the amount of time that it takes for it to make its orbit, right? That was Kepler's third law of planetary motion. The square of the orbital period is equal to the cube of the average distance, or the semi-major axis. And so we can get an idea of how far a planet is from its companion star by how long it takes for a star's light to go through a redshift, blueshift cycle. And also, spoiler alert for coming lectures, for a main sequence star, its color will tell you how big and how hot and how also massive it is, right? And so we can get an idea of how massive the planet is by how much the light red shifts and blue shifts, right, as it goes in a cycle. So long story short, we can use the Doppler effect in order to try to look for planets orbiting other stars. Now, most of the planets that we've been able to detect are very massive planets that are very close to the star, right? Because then the force of gravity is greater and it's much easier to detect planets that are both more massive and closer to their companion star, right? Makes a lot of sense. So much so that we have kind of a word for really, really massive planets that are really close to their companion star. We call them hot Jupiters. Obviously hot because if a planet is very, very close to its companion star, then it's going to be hot. And then Jupiter, of course, is the most massive planet in our solar system, the gas giant. And so we call these planets hot Jupiters. In any case, once we believe we have detected one of these planets, or maybe more than one, we found several in some solar systems, by this Doppler shift method, that's not really necessarily conclusive evidence by itself. And so what we do is we try to look to see if the planet is going to go in front of the star. Now, I'm going to erase all of this here. Remember, planets don't make their own light, and so let's say we got a big star here, right? And then we got a tiny little planet, and it's making this orbit like this around the star. And as this planet goes in front of the star, it's going to block out just a little bit of the light from that star, right? Now, if you were looking at the amount of light, the brightness of this star, right? Let's say that here's our luminosity, whatever you want to call it, and then here, over the course of time, it's going to be a certain amount, and then when the planet goes in front of the star, it's going to dip just a little bit, right? And then as it goes past it on the other side, it should get brighter again. And we'll see just kind of a dip, like this bathtub-looking portion of a light curve. And if, every so often, whenever the planet is supposed to have gone around it, if the bathtub repeats, then we know we've confirmed that there is indeed a planet orbiting this star, right? If we can predict when this bathtub is going to happen again, according to our model of the planet pulling the star around, right, our Doppler shift, then we say we've detected what we call a transit when the planet goes in front of the star. Anyway, this is what I did when I worked at NASA. I looked for planetary transits in the southern hemisphere sky with a telescope in Chile. In any case, when a planet goes in front of a star like that, or when something goes in front of something else, we call that an occultation. And that comes from the same word that the occult comes from. The occult was something that's hidden, right? And this planet is hiding part of the star's light, right? In any case, we have a better chance of detecting planets that have a solar system that's got, its accretion disk that eventually turned to all their planets, that if all their planetary system is kind of like facing toward us, right? We say the m sine I, or the mass of the planets, times the sine of the angle in between our line of sight and the star is close to 90 degrees, right? If we're looking straight at the line where all the planets kind of orbit around the star in a plane, then we'll be able to see those planets dim the light from the star more easily. Now, I know that sounds like some crazy kind of like science fiction. But this is actually the truth. And as a matter of fact, we've been able to discover a lot of planets this way. And I'm trying to look up, there's actually a database. I'm trying to find it here. We found something like almost 2,700 planets so far, and I think something like almost 100 of them are thought to be similar to Earth. And so, in order to do this, of course, we launched what we call the Kepler mission, right? We put a space telescope out into space. And the Kepler mission actually just ended a few years ago, and then we've got another one going up, and its results have not really come in conclusively as of yet, but it should find even more because it's an even better telescope than the last one we put out. Now, as a result of us putting this fancy equipment out into space, right, we have, telescopes out into space, things like the Hubble and the Kepler mission, so on. We've finally been able to look at and take pictures of planets, just taking pictures, direct images of planets, what we call exoplanets or extrasolar planets, planets orbiting other stars. And there's quite a lot of them, actually. I forget how many we've taken as of now, but there are quite a few. I think it's over 30 now. The first one was Fomalhaut B, and we started taking pictures of that, I think, in 2008, but it wasn't until 2012, I think, that we finally were able to prove that what we're taking pictures of was a planet. And there's an image of that also in today's image bank. But we're finally starting to be able to take direct pictures of planets orbiting other stars, which is pretty neat. They're not very good right now, they just kind of look like pixels, but we'll get there. The better our technology gets, the better our images are going to get. Okay, that about does it for today. If you have any questions, of course, get a hold of me through the normal channels. And I hope you have enjoyed today's lecture as much as I have enjoyed giving it. And I'll see you next time.